have to combine the left and the right to see, like subtract mg from the left and the right, and then that wouldn't cancel out anything.
No.
Would you rearrange the equation so that one of the unknowns is on one side and then use that component on the opposite side in the original formula?
Let's just do that quickly. Let's see what happens on that one.
Yeah.
So if I have y is equal to m, so y would be equal to mv squared over r minus mg. And then you're suggesting put that into here?
I was past tense suggesting that.
Now, if you do that and you come out with 0 equals 0 or 1 equals 1, then you know you've done something right. It doesn't necessarily help you at all. It doesn't help you at all, other than the fact that you can pat yourself on the back for having done some math correctly, but it's not gonna help.
I see that.
What if we put, what if we multiply both sides by r and then get rid of the m so we can get both unknowns on one side?
We give it to the math people.
All right, so we can manipulate one equation all we want to, but we still have two unknowns.
Yeah.
Get rid of one of them.
How do you get rid of one of them?
Make it one?
Another equation, right?
Not that way, pardon?
We need another equation to
Like
work with?
quadratic.
No, we need to think about the problem.
Hmm.
Sorry, spoil it. What is the problem asking?
For
For speed.
speed.
That in order for what to happen?
Oh. Yeah, we need some normal force, because if the normal force is not intact, then the car will fall. So we can plug in a number for normal force.
What would you plug in? It's not a random number.
Is it the force of gravity?
No,
No, because it's acting this way on the car, and we don't want the car to fall down at all.
correct?
So would we plug in 0?
Yes. Because if you're going below the minimum speed, it's coming off the track. And normal force is 0 if it's not on the track anymore. We're looking for that minimum speed where it's just barely touching. The normal force is as small as you can make it. In other words, 0. So from the context of the problem, the normal force is practically non-existent. Now technically, given the wording of the problem, it's still touching the track, but so barely that it becomes a negligible amount.
So we're saying normal force is negligible.
Yes. If you're at the minimum speed. If you're above the minimum speed, then you're pressing up against the track, the normal force will be above 0. If you're below the minimum speed, you're falling off the track, and normal force is absolutely 0. But since we're looking for that minimum speed, that normal force is tiny.
That kind of makes sense.
Okay.
Is that also known as the X is small approximation, or is that something completely different?
The what again?
X is small, it deals with chemistry as well. Where you have, if X is incredibly small, you just act as though it's 0.
Oh, yeah, that,
Okay,
yeah, we're definitely doing that.
okay.
I think I have my logic backwards. I see where I got 0, but it seems like if the normal force were greater than 0, like if it were a positive number, then, well, I get now.
No, then it would be pushing it up onto the track if normal force was greater than 0. If it's about 0, then it's not really doing anything.
Right,
And then,
okay.
And I would tack
Okay,
onto
I
that,
figured it out.
the only way that it would be pressing, that normal force would be above 0 is if the car's going faster than it has to.
Yeah, okay. Okay. I got
that
it.
makes sense, but I feel like if I had to do a problem involving this, I wouldn't be able to, like, directly pull that.
Well, hopefully you can get at least this far. Show me your work as you go. So now we're left with the simplification of G is v squared over r. In other words, we're at the peak there. The acceleration due to gravity is the centripetal acceleration. And so v is just the square root of gr. which is square root of 9.8 times 50, which is
22.134. Well, it was 13368.474.
that's not the pause.
Oh, newtons,
22.13.
Meters per second.
meters per second.
Yep, it's a speed.
Gotcha.
I got like the same thing, but it's like a slightly different decimal. It's like 1.36.
Yeah, I got that too.
You had 21.36 or
22.
22.136?
Yes.
What happened?
What?
Our calculators
It's
are
about
tripping.
I also got
1,000th of
So
a.
did I.
That's weird.
Your calculator's tripping.
I don't know.
Suddenly, the Shuttle Challenger has
I'm looking.
exploded.
I'm looking at it. 9798 times 50. That's
Oh.
448.
Oh.
That's the difference.
Yeah, we
just
use-
use 9.8.
Yeah.
Oh. Well, I just used more decimal places.
you're-
Yeah,
so.
you
Yours
got,
is
you got
actually-
technical with it.
It's actually more accurate than us.
Well, it depends on where
If
you
you
use
were
it,
to
it could be
say-
less accurate.
Okay.
9.8 is definitely an average for like the 15th degree latitude. Right? Is that what
Oh.
it's set for?
I'm not sure because there's so many variations if we're going into, I think Rome is 9.800,
Yeah.
although it's not just like everywhere that in Rome.
There's less gravity in Rome? Or did you say more?
Well, compared to Winston-Salem, I think Rome's, you would weigh slightly more.
I'm gonna backtrack a bit. Where did mass go? You went from like,
Once we got rid of the normal force, then I have mass in every term, I can cancel it out, I can divide by mass and it goes away.
okay, I see.
If you don't like doing that, feel free to stick in 1,000.
But like it's gonna cancel out anyways. Okay.
Yep.
Yeah, so how did we get from, so we went from the y plus weight equals mass times acceleration. Why did you include the mv squared with the r below?
Once we get the first equation of motions, our first version of it, we then substitute in formulas for which we have independent equations. We have an independent equation for weight. Weight is equal to mg. We have an independent equation for centripetal acceleration. Centripetal acceleration is either v squared over r or omega squared r.
And we chose the v squared over, oh, okay, and you multiplied it by mass, and that's why you have both of them.
Yeah, so technically, m times v squared over r,
Oh, okay,
which
that's
is
all.
that.
Okay.
So other questions?
Wait, and I'm sorry to like take you back, but, so we said that the normal force is 0. Why?
I suppose there's a bucket line around here. Oh, you know what, we'll use these. Alright. So, as I swing this thing around, it's going in a circle, close enough. Now I can slow down, I don't have to be at that speed in order for it to make it. I can keep slowing down, at some point it's going to fall. There we go, start to get the jerk. Similar type thing here, the car is going, if the car's going 1,000,000 miles an hour, it's a board problem, it can do that. 1,000,000 miles an hour, it's gonna make it around that loop, no problem whatsoever, assuming the loop doesn't get destroyed. But as it does that, because it's going so fast, there's this extra force from the track to keep it traveling. The track weren't there, that car would go shooting off into space. Just like if the string broke, the stopper is gonna go shooting off. Now, if I'm at that minimum speed, well, actually, in this particular case, when it's at the peak, I have two forces acting on it. There's tension in the string and weight of the stopper itself. As I slow down to try to find that minimum speed, the tension is getting smaller and smaller. I can feel it in my hands that there's less tension in it. The analog over here is the fact that as you slow down, there's less and less normal force. The track doesn't need to hold you in as tightly since you're traveling slower. And since the normal force is getting smaller and smaller, so that minimum speed happens when that normal force is zero. Or by cause and effect, I think we're backwards there, but. Normal force is zero when I'm traveling that minimum speed. All right, any other questions at the moment?
Would that technically fulfill Newton's third law of like equal and opposite forces? Well,
Yeah, well, this force also, this goes to zero also.
right, because there's like nothing, right, okay.
Yeah. Newton's third law is not a relationship between these two, it's a relationship between those
Yeah.
two. I figured you sort of had it at that point, but I felt the need to throw that in. For those who weren't asking the question.
That was me, I wasn't asking the question.
Okay, that was for Henry.
Thank goodness.
All right, I'm about to erase this and we're about to start with something new.
Chapter 7?
Yes. Because there's another question I could have asked here, which we don't have the capability of answering yet, we have to do 7 first. But if the vehicle starts at rest, how high up does the vehicle need to be in order to make it around the curve?
Would we be able to answer right now if there was like a device that would like push the cart from rest? Like if it were shot out of a cannon, would we be able to answer that?
Yeah, I still have to give you a little bit more information. Now with the next chapter, we could then add onto it, it's being propelled by a tight spring with a certain, and I can give you the spring constant, which tells you how stiff the spring is. And then the question is, how much does the spring need to be compressed in order to get the car up to there? But that's still chapter 7 stuff. But the first thing we're gonna do here for chapter 7 is to, what hopefully will not become a read my mind exercise. So we're gonna start out with a scenario of a collision. I have 2 objects, they're gonna come towards each other. So we got the visual here, and then I'm gonna draw an absolutely spectacular drawing on the board, you know, my typical style. They're coming towards each other, they are going to collide. They stay in contact for a bit, and then they separate. In this particular scenario, I'm gonna have them bounce off, but they don't necessarily have to. If this were, say, a truck and a fly, the same thing happens, it's just that they will collide, they will stay in contact longer if it's a bug and a truck. But I'm gonna have them separate in the scenario. So we're gonna start out with A, traveling to the right, and B, traveling to the left. This dotted line here is an indication of where they will actually first meet. They will be in contact for a bit. And then they will separate.
Are we still assuming this is a bug in a truck, or is this just 2 random objects?
Just 2 random objects.
Okay. But we are assuming that the system has shifted to the left during the contact.
Yeah, there is some movement while they're touching.
Okay.
Now, while the contact is happening, there are 3 things that are the same for both of them, for object A and object B. So there are 3 measurable quantities for A and B while they are in contact. And just to add an element of excitement, can you do it before the man gets hanged?
Velocity?
Yeah, I was gonna say distance.
All right, so I heard velocity first. They're definitely not going the same velocity
Yeah.
at that point right there. B is going to, given the scenario, B slows down and A changes directions completely. So at some point, the velocity of A is 0, but B does not get to be 0. So it's not the same. And so we just put a little velocity over there.
Oh, I thought you said during the point when they're contacted.
Yeah. B keeps traveling to the left, A turns around. Since A turns around, the velocity of A has to be 0 at some point.
But B also eventually turns around, because it's going back this way.
It turns around at this point, A turns around
Yeah,
There.
somewhere else.
Okay,
The
so we're
displacements are
including the
different.
moment of contact in,
You say moment, contact happens over there's a duration there, it's not instantaneous.
well, I was just thinking that when both of the boxes are already touched and they're moving, they share the same velocity, but if you include the point when they smack together first, then,
When they smack together first, that's still part of the contact.
you know,
Distance.
Ooh,
What do you mean?
Like, when they start,
As in this and this?
yeah.
No.
Oh, sorry, guys.
okay, good. Velocity is like distance over time, so even
Right.
if distance was the same,
Oh, yeah.
velocity would have had to have been the same.
Also, another thing on velocity is they start out initially traveling in a different direction, so at the point of contact, they would still have to be moving
That way, yeah.
opposite directions, the velocity could not be the same.
Is time one of them? The same length of time for each of them if they're in contact?
And strangely, time is the one that most groups never figure out, which usually gets me to throw in my possibly most obscure clue ever of, it's the name of a Bobby Sherman song, which usually prompts students to go, who?
did you just say Pink Floyd?
I could have gone Pink Floyd.
Time.
I had a student a number of years ago who actually had seen Bobby Sherman in concert.
Wow.
Yeah, it's pretty amazing because the guy was obviously older than I was. His sister was a fan. Anyway, Amy,
Weight, mass.
mass is not necessarily the same.
Alright,
It's
let's,
funny that his leg is longer than his body.
let's think about this before the man gets angry.
Before, yeah,
So they can't have the same distance or velocity, so that means acceleration can't be the same because those are in congruence with each other. The only thing we have that's the same is time. And mass is definitely not the same because they're two different objects. It could be a truck or a fly, and at the same time that they're colliding, they're gonna split off at some point.
and like one's moving to the, like B has a bigger force.
Yeah.
Obviously, because it's like pushing to the.
So force can't be the same.
What about the force due to gravity?
There's no mention of a planet anywhere in
Yeah.
this.
So it's
About
just
This
irrelevant.
is in space.
It's irrelevant.
Yeah.
the normal force that they push on
There's a
something.
different one.
Close,
The opposite directions, but say magnitude?
yes. Magnitude of the force is the same.
Yes.
So I'm gonna write that as the force on A from B. No vector symbol over it, this is just the magnitude of, actually, let's go ahead and do magnitude. This is the force on B from A.
Okay, interesting.
All right, so we got the magnitude of the force and time. Another thing, Brooke, earlier when you said distance, that's actually before the collision, what the distance you were talking about.
Yeah, that's what I was talking about, and then I realized we're talking about like the contact.
But it's still got a torso.
So, distance and position would be basically the same thing, right?
Why
I
would they be
mean,
the same thing?
well, your displacement would be your position over time. So, but in that
Whoa,
moment,
whoa, 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 whoa. Let's work on the language.
okay, displacement is, distance over time?
Nope.
That's what I just said, isn't it?
Velocity over change in time, isn't it?
Oh, change in position over change in time.
That would be velocity.
Displacement is change in velocity over change in time, right?
Is time involved in either of those?
Suddenly, there's something
Hold
that's
on.
being thrown about.
Hold on,
What was the
hold on.
last thing you said again?
The change in velocity over change in time?
Is acceleration.
That's exactly.
So displacement is just change in position.
Yes,
Right.
Okay.
yeah. So are you still sort of
Chapter
ruminating, or are you throwing that out there as?
I'm thinking we're only talking about when they meet, right?
Well, while they're meeting.
While they're meeting. But their positions, their displacements aren't the same, but their positions are, cause they move as a group, right?
But generally, when you talk about the position of an object, this is a realistic two-dimensional object here.
Yeah.
When you talk about position of an object, you generally are talking about the position of the center of mass.
Yeah. So they
So
have two
the
different-
positions
Yeah, okay.
are not the same. I guess I chimed in before you actually offered that one, so I'll bear a body part on that.
The hangman thinks you.
Then would you say displacement during contact is the same?
A goes from there to there,
Yeah.
B goes from there to there. Displacement is the other one. Wow, I guess I shouldn't be surprised, that was a lot faster than most groups take. All right, so, why? What's the point of this? If I combine these two things right here, combine these two concepts, we end up with this idea of impulse and momentum. Chapter 8. If we combine these two concepts, we get the idea of work and energy, which is chapter 7. So that's chapter 7, this is chapter 8.
Is that the work energy is from the forces to the displacement? Or is that time to displacement?
Work and energy is when you combine force and displacement, you start dealing with work and energy.
Okay.
If you combine force and time, you get impulse, which is related to the change in momentum. Therefore, use this as a segue, let's talk about what work actually is. And the person was spared, at least. You know, you say he wasn't hung, but most of his body was still there. I'm not quite sure he would survive it.
I think all that matters is the head.
Yeah.
That's why it's kind of funny when you start with the head.
Of course, we're already putting a decapitated head right there on the diagram,
Yeah.
so I think he's dead before he even makes it.